Hi everyone, Mr. Boltri here bringing you video 5.3. We're going to be talking about how to calculate the moment of inertia for various objects. So first we're going to review some examples that we hopefully talked about in class today. We're going to introduce the parallel axis theorem, talk about another example, the uniform solid cylinder, and then just talk about other various shapes that you might be asked to calculate or compare the moment of inertia for. So first, the thin hoop. As always, we start with our general equation, calculus equation for the moment of inertia as the integral of the r squared dm, where r is the distance from the axis of rotation to the mass of the object that we were talking about, that little chunk of mass dm. So in this situation, all of the chunks of mass are the same distance away from the axis of rotation. So we can actually just take out that r squared because it's always going to be capital R, big R, squared. And then if we integrate all the dm's, that's just going to give us the mass of the object. So the thin hoop is easiest, and this is definitely worth memorizing, just having sort of at the top of your head, easily accessible. It's not on your formula sheet, but this is worth just knowing so you can solve thin hoop problems very easily. Next, a thin rod, which is rotated about the center of mass. We start from the same place. And in this circumstance, we have to use the linear mass density formula, which is, so if we were given the mass density of this rod, we can say that the linear mass density equals the mass divided by the length. But really what's going on is at any length, then we know sort of the rate of change of the mass, the little dm over dx is what, if we're given the linear mass density, either constant or changing, then that gives us our dm over dx. And then we can do some algebra rearrangement to solve for dm in terms of lambda and dx. So then what we can do is we can, so that would be dx times lambda equals, man, I really wish I had shown those steps out. Oh, but we did this in class today, so it's not really that big of a deal. So then we know that we can factor out the m over L because they are not changing with respect to x. These are just constants in terms of the problem. And you'll notice that I have this big space here so that we can add our bounds of integration. And so it's integrated. If this is our 0, if this is our center, then it goes from negative L over 2 to L over 2. We can do the calculus on that to find the antiderivative, the definite integral. Then we can, now it's just a matter of simplification to get the moment of inertia equals 1/12 times the mass times the length squared. So this is one that you don't have to memorize, but you do have to be able to show the derivation here. Probably the trickiest step of the derivation is getting from this dm to the dx, and that goes through lambda, the linear mass density. So this is definitely important and worth knowing. In a similar problem, if we then take that rod and rotate it, instead of rotating it about its center, we rotate it about one of its ends, then just by thinking about it, that's going to increase the moment of inertia because now there's going to be more mass that's farther away from that axis. And since it's the x squared, then it's going to have a bigger impact. So we're going to use the same initial setup, but we're just going to have different bounds of integration. Now, if this is our 0, then one of the edges of the rod is at 0 and the other edge of the rod is at L. So it's from 0 to L. Do the calculus on that, and then we find that it's 1/3 ml squared, or mass times the length squared, which you'll notice is a much larger number than 1/12 times the mass times the length squared because of that mass, which is now so far away from the axis of rotation. So this was the equation for the thin rod about its center and thin rod about its end. But let's say that you forgot the 1/3 mass times length squared, and you were asked to prove it. And especially, here's a new thing I'm going to teach you. The parallel axis theorem is pretty cool. It's a way for you to figure out the moment of inertia of an object if you're given the moment of the inertia of that object around its center of mass, or vice versa. So we can use this to figure out the moment of inertia on a different axis of rotation, using the parallel axis theorem, which is given as this. So I can find the moment of inertia for a new axis so long as we are given the moment of inertia around the center of mass and those two are parallel. So it wouldn't make sense if we're rotating one thing this way and then another thing this way. But because these two are parallel, we can find the new moment of inertia by taking the moment of inertia around the center of mass, which would be this one, and then adding the mass of the object times the distance squared from the old center of mass to the new center of mass. So for example, in this example, the old center of mass was in the middle and the new center of mass is at the end, that D is going to be L over 2. So if we plug in our numbers, this is our original center of mass as given. This would be given to you, for example, in the problem. And then if we scooch the axis of rotation down half the length of the rod, L over 2, we can do the math on that, add these two together, and find that the new moment of inertia for the rod when we spin it around the end of the rod is 1/3 times the mass times the length squared, which is exactly what we just talked about on the previous slide. So this sort of shows that the parallel axis theorem works out. I'm using an example that we've already done, but it's going to be a really useful tool if you're, for example, given an example that we haven't done. If you're given the moment of inertia around the center of mass and this other information, then you can find the new moment of inertia. So that's a really useful formula that you're going to want to have in your tool belt. Okay, let's do one more of these proofs for moment of inertia calculations for objects. This is sort of in terms of what you need to know for AP. These are the big four that you need to know: the hoop, the rod, the other rod, and then the cylinder. So these are kind of the big four that you need to know. And also you just sort of need to know the general process. So we're going to go through the general process for this one right now. So if we have a uniform solid cylinder that's going to have a constant density, and we want to find the moment of inertia when it's rotated around this z-axis, which is straight through the center. So rotated sort of like this in the image. So we need to find the moment of inertia in order to be able to calculate a whole bunch of things. So first, the word uniform is doing a lot of work in this problem. It means uniform density, which means that the mass divided by the volume is going to be uniform. So any chunk of mass divided by a chunk of volume is also going to have that same rho, that uniform volumetric mass density. Okay, so then what I can do is I can take and rearrange this equation in terms of, so I can solve for my dm in terms of rho and dv, which is good because then I can substitute this into my original equation for dm involving rho, excuse me, and dv. Except I don't really want it in terms of v, I want it in terms of r. So now I'm going to look at this little cylinder that I've chopped out. This is going to be my dv, this yellow circle that goes all the way down. So I need to figure out what is the volume of that little, it's going to look kind of like a toilet paper roll. What is the volume of the toilet paper roll? Well, or my little chunk of volume. What is the volume of this little chunk of volume? We're going to do kind of a pi r squared to get the circumference times the height, which is going to be L, and then times the thickness, which is going to be dr. So I can say pi r squared L, which is like basically the surface area, the circumference, the surface area of this toilet paper roll, times dr, the thickness of that toilet paper roll. And so now this is really helpful because now we have dm in terms of dr, and we can substitute it back into our original equation. Let's go ahead and do that, and we can factor out the things that are not changing with respect to dx or dr. I'm using dx's here, but you could just as easily use drs. In this circumstance, they're pretty much interchangeable. So the density is not changing with respect to x or r, neither is 2 pi, neither is L. So I can factor all those out. And I'm left with a antiderivative, which I can actually do the math for. So when you do the math for this, you get the volumetric mass density times 2 pi L times the radius, the whole radius to the fourth divided by 4. But this is not going to be something that I'm going to want to use formulas for. So what you can actually do is this rho, we can actually is equal to the mass divided by the whole mass divided by the whole volume. So the whole volume of this whole shape is going to be pi r squared, which is the area of this top circle times L is the volume, pi r squared L, in which I can then substitute this mass divided by pi r squared L in for rho right here. Then when we look at what cancels, so my pi's cancel, my r squared and r to the fourth, it leaves me with r squared. My L's cancel. This 2 divided by 4 is 1/2, and I get that the moment of inertia equals 1/2 times the mass times the radius squared. So that is another derivation for another formula, this one for a uniform solid cylinder, which relied mostly on, you're probably going to notice the pattern here is that we are really relying on our volumetric mass density formula or our linear mass density formula to solve these problems. So these are two formulas that you're really going to want to know how to use and manipulate with the goal of substituting into our general moment of inertia equation to substitute out dm for dx or dr or something that's going to be useful for us. So now let's talk about some other shapes that you might need to calculate the moment of inertia for. So we've already talked about a thin hollow cylinder versus a solid cylinder. And if you look, the thin solid cylinder, the moment of inertia is mass times the radius squared, and the solid cylinder is 1/2 times the mass times the radius squared. And we can think about the definition of moment of inertia to make sure that that makes sense, because the hollow cylinder, more of the mass is farther away from that axis of rotation. So it would make sense that it would have a higher moment of inertia. Similar thing, we did the thin rod about one of its ends versus the thin rod about the center of mass. And in this example also, we noticed that in the example where there's more mass that's farther away from the axis of rotation, it's going to have a higher moment of inertia, whereas if the mass is closer to the axis of rotation, it's going to have a lower moment of inertia. So you're going to have to be able to do these sort of comparisons with other objects, maybe ones that you haven't even seen before. For example, if we were to talk about a thin hollow sphere versus a solid sphere, then you should be able to say that the thin hollow sphere should have a higher moment of inertia than the solid sphere because it has more mass farther away from the axis of rotation. So you're going to need to be able to do these kind of comparisons. So you're going to need to know how to derive these 1, 2, 3, 4 equations. And then if you're given a new shape like spheres, you're going to need to know how to compare them just sort of qualitatively, comparatively. I haven't seen the need for you to know and derive this formula or this formula. And I'll let you know if I see anything that makes me want to amend that statement. So this has been a lot of calculus, a lot of math, and I'm looking forward to sort of practicing applications of this in our next class. But for now, this is Mr. Boltri wrapping up video 5.3 on calculating moment of inertia, and go Bears.